Hi, I am Hussein Adeli, and I'm presenting our work with So-Young An and Greg Zelinsky titled Learning Object-Centric Attention Using a Recurrent Dorsal Ventral Neural Network. Attention control refers to our ability to prioritize and select relevant information in the sensory input and is essential for goal-directed behavior. Eye movements have been long used to measure the attention behavior, and here are a few examples of such behavior in everyday tasks: searching, reading, browsing a website, and answering questions about a visual scene. Performing these tasks requires integrating attentional modulation with object recognition, as objects are typically the units of selection and the representation drives the attention control. Integrated object recognition and attention planning in the brain is shown to rely on the interaction between the two visual pathways, with the ventral what pathway involved in feature processing and recognizing objects and scenes, and the dorsal where pathway involved in the spatial prioritization of visual input and the guidance of actions to objects. The model on the right shows an early attempt at formalizing this interaction. As objects are how people interact with the world, they are attended, tracked, recognized, and compared with each other. Recent works have examined how object-centric representation can be captured in neural networks. Most of the ideas revolve around object files, where object representations can be encapsulated in a given slot. The development in this domain or capsule network is shown up top that employ category slot to represent objects. Bringing these ideas together, we built Okra, an object-centric recurrent attention model. This model is based on the encoder-decoder framework, where the processing along the encoder can be mapped onto the ventral pathway. In our model, a hierarchy of convolutional, recurrent, and capsule layers provide an object-centric representation of the glimpse input. Then this object-centric representation can feed to the decoder mapping onto the dorsal pathway, which provides top-down attentional modulation for the processing in the ventral pathway. The encoding and decoding steps are taken iteratively. Cycle of prioritization and selection repeats, with the model glimpsing different objects and reconstructing the image gradually. The attention mechanism in Okra is based on the differentiable glimpse mechanism from draw. The attention window is a grid of filters applied to a small or a large area of the image. However, because the number of filters covering the attention window remains constant, as the window gets bigger, it samples increasingly low-resolution information, creating a trade-off between the size of the attention window and the resolution of the information extracted. This property is aligned with Zoomlin's theories of human attention. The accumulated capsule length at the end are used for predicting the object classes. A margin loss for classification, along with the reconstruction loss from the cumulative campus, are used for training the model. The multi-step process in the model is shown here on a sample image from a MultiMNIST cluttered test. The images are generated from placing 2 randomly selected digits and 6 clutter pieces from other digits on a blank canvas. Okra's read attention is overlaid on the image in the first row. The second row shows the red glimpse in image dimensions at each step. The model starts with a wider attention window and samples low-resolution information from the image, and with subsequent glimpses, the model detects, recognizes, and routes only the object-centric representation for the 2 objects as displayed in the gradual reconstruction. A more dynamic behavior of the model is shown at the bottom on 2 sample images. We tested Okra on recognizing highly overlapping MNIST digits. The dataset is generated by overlaying 2 digits and shifting them up to 4 pixels in each direction, resulting in images with 80% overlap between the 2 bounding boxes on average. Examples of the model recognizing the 2 digits correctly along with the reconstructions are shown on the bottom left. The bottom right shows sample errors the model made. Our model outperforms the original capsule network model while having almost a third of the number of parameters and being trained on a set that is 20 times smaller. we saw a clear effect with the number of glimpses on the model accuracy. We then started with the 3-glimpse model and probed different components of the model to measure their impact on the accuracy in this test. The biggest effects we saw in the task were from removing the glimpse mechanism or the recurrence. Taken together, the results showed that while recurrent computation can be effective for challenging recognition tasks with high degrees of occlusion, when it is paired with an attention glimpse mechanism, more compact and better performing models can be built. We also tested our model on the SVHN dataset, consisting of real-world images of house numbers, each containing a sequence of 1 to 5 digits. These figures show the model behavior for sample images, as it glimpses, recognizes, and reconstructs the objects in the sequence. We then tested Okra on a MultiMNIST tracking task, where the model only sees 5 frames of the visual input and is supposed to recognize the 2 digits and project their trajectory up to 15 frames into the future. The model learned to maintain the 2 objects in its glimpse window, and through object-based representation, predict each object's trajectory. Finally, we tested our model on relational reasoning using the synthetic visual reasoning task. The model achieved accuracies on the level of very deep models such as ResNet and DenseNet on this task, while being much smaller, again relying on its object-centric recurrent attention mechanisms. In summary, we believe that encoder-decoder models provide a useful framework for building integrated attention recognition models. And attentional glimpses can further improve the accuracy of the models beyond using only recurrence. And using our model, we showed that pairing object-centric representation with recurrent attention can help us build models for object detection, recognition, tracking, and visual reasoning.